you for staying with me here. You'll see that I kind of got us started here already by writing out the equation. How did I get that? It says, well, in a certain experiment, 28 milliliters of 0.25 molar HNO3 and 53 milliliters of 0.32, this should be molar, forget that milliliters, KOH are mixed. And then it says, so that gives us our reactants. So HNO3, KOH, both reactants. It says calculate the amount of water formed, so that tells us that that's a product, and then we can predict the other product just like we did when we were doing the precipitation reactions. But now let's take a look at the questions that they're really asking us to do, because there's actually two problems here. They want us to calculate the amount of water formed in the resulting reaction, and they want us to calculate the amount of OH minus ions or H plus ions that are in excess after the reaction goes to completion. So hopefully you'll notice, because we are given two different starting points, you'll automatically think, this is a limiting reactant problem. Now, limiting reactant problems do look different when you're talking about acids and bases, but hopefully this will make sense once we get into it. All right, since this is a limiting reactant problem, we start with one of our reactants. In this case, we'll start with HNO3 because it's listed first, so why not? Now, I do apologize. I am going to try using my finger as my stylus, as my stylus is not working very well today. But we'll start with what we can start with. Again, molarity conversion factor. So you have to start with the 28 milliliters of HNO3. Then you use your molarity as a conversion factor. So for every 1,000 milliliters of HNO3, we get 28 milliliters, 0.25 moles of HNO3. That's an H, really it is. And then using our mole to mole ratio, we know that for every mole of HNO3, we're going to get 1 mole of water. But now you might be thinking to yourself, how do we know that's where we stop? Because they're talking about amount. Well, remember that there's many different ways to figure out amounts. Amounts can be moles, amounts can be grams, amounts could be milliliters. And honestly, you could continue to figure out how many grams. You just use the molar mass of water. You could continue on then after that to use density in order to find out the number of milliliters, because you know the density of water. But we're not going to do any of that. We're just going to stick to moles because it works. And as long as they say amount and they don't clarify, that's the easiest one to get to. So if we take 28 times 0.25, or a quarter of 28, which is 7, divided by 1,000, we get 0.007 moles of HOH, which, remember, is just the other way to write water. All right, so then we can also start with KOH. But when we start with KOH, we're going to start with 53 milliliters of it. And in 1,000 milliliters of KOH, we actually get 0.32 moles of KOH. And we know that for every mole of KOH, using our coefficients, we get 1 mole of HOH. And so we end up with 53 times 0.32 divided by 1,000, which, using rounding and such, comes to 0.017 moles. All right, so using what you know about limiting reactants, hopefully you can tell that 0.007 moles of HOH is all we're going to get out of this reaction. That means that HNO3 is our limiting reactant. And because HNO3 is our limiting reactant, that means that it's not going to be H plus left over, it's going to be OH minus left over. Why? Because it's KOH that's left over. So let's take a look at how we can most easily figure out how many OH minus ions are left over. Now, a lot of you will remember from when you did the last unit's assessment that there's more than one way to figure out how much is left over after reaction. There's 3, 4, 5 different ways. In this case, because we're looking for a specific concentration of an ion, it's going to be an even different way. Let's look at it this way. When we have 0.007 moles of HOH, hopefully, remembering that this is really H and OH minus, you will see that the concentration of OH minus is 0.0, or not the concentration, the amount of moles of OH minus is 0.007 moles of OH minus. Likewise, we could have had we used all of the KOH, we could have had 0.017 moles of OH. So, if this is what we could have had, what might have been right here, this is what might have been, and this is what we did get, if we subtract them, that should tell us how much OH minus is left over. Now, I know that it's written in the wrong order, so you're really subtracting the top one from the bottom one and not vice versa. But hopefully you see that that means that we have 0.01 moles of OH minus left over, because we only got 0.007 moles of that 0.017 potential. All right, so that tells us moles. That doesn't tell us concentration. Remember that concentration or molarity is really the moles over volume. And we have the moles already. We have 0.01 moles. But what is our volume? Well, if we take a look at what we mixed together, we mixed 28 milliliters of HNO3 and 53 milliliters of KOH together. So that means we actually mixed 81 milliliters of stuff together. Remember though, we don't want to have milliliters, we want it in liters, so we need to convert that. Oops, I kind of forgot the one there. So now if we do that math, we have 0.01 divided by 0.081, and we find that the concentration, well, that's kind of fun if you put that on your calculator, is 0.123 of OH minus. And if you actually, the reason why I said it was fun is if you put it on your calculator, you get 0.1234567900123. It's kind of interesting. Fun numbers. All right, so that gives us the concentration of OH minus that is left over. All right, now if we move on, we're going to move into a different topic. So I'm actually going to start with a separate video.